I'm not sure what you expected coming into this talk, but I'm really glad you're here. This has been probably one of the most difficult talks for me to write. It distills about over a year of efforts in structural change in our company, and it's really hard to distill. So bear with me. The title's Rearchitecting Toward Resilience. We'll talk about what those things mean as we go. But just to give a little bit more background about me, this is my best friend, Joe DeVivo, and I, wondering what the big deal is about monads. If you find out what the big deal is, let me know. I currently work at BlockFi. My title is the Director of Product Delivery, but that basically means I'm a very senior engineer and sometimes I lead teams. I previously, as Amos mentioned, I worked at Basho. I also worked Comcast and Postmates. In the Beam community, the two things I think I'm most proud of is my first big project in Erlang was creating a parser generator called Neotoma. I have tried to rewrite it about 5 times and failed. So I kind of give up on that, but it's fun. Also, there's a little tiny library I wrote a while back called eUnit formatters that is now included in Rebar 3. So if you're on Rebar 3 to run your unit tests that are with eUnit, the ANSI colored progress output is from eUnit formatters. As Amos mentioned, I help him organize the Kansas City Elixir meetup. We find speakers and we build the community. It's great fun. And I do have 4 cats. One of them is in the room with me, so you may see her prance across the screen while I'm talking. Also, I happen to be a meme somehow. If you search the internet enough, you'll find in 2014 there were a lot of pictures of me holding things. Thanks to Joe, who was on the previous slide, and some other folks who couldn't help themselves. So after the talk, go search the internet. It's great fun. Okay, so I'm going to be talking about our structural changes we are making at BlockFi. And BlockFi, for those who don't know about it, we're a financial services company for folks who hold cryptocurrency. You could call it wealth management, is another term we use. So what does this mean? We have a number of products, financial products. The first one that we offered was crypto-backed loans. So if you think of a traditional loan, you provide collateral that secures the value of the loan. So, a good example is a mortgage on a house. You're trying to buy a house. The house becomes collateral as a physical asset to back the loan so that the bank has something to fall back on that has value if you default. Well, we do the same thing with cryptocurrency. If you bring cryptocurrency onto our platform, we track the notional value of that cryptocurrency. So what does it mean in US dollars or euros or whatever? And that is used to secure a cash loan that we make to you. In some jurisdictions, and this is an area that is changing, so I can't speak directly to whether your jurisdiction has it, but we do have interest-bearing accounts. So if you put cryptocurrency onto our platform, you will earn interest on it. And it's a nice way to make use of your cryptocurrency instead of just letting it sit there. We allow you to trade on platform to different kinds of cryptocurrency. This is a first party trade. This is not trading with peers. So when you're trading this, you're trading with BlockFi, you're basically buying the other cryptocurrency using the cryptocurrency you have on the platform. And finally, this is our first really big consumer direct product, as we have a Bitcoin rewards credit card. So instead of earning airline miles or hotel points or something like that, you can earn Bitcoin. And pretty soon, I think we're going to offer other types of cryptocurrency you can earn just by spending money with a credit card, a traditional credit card. So that's what our business is. Why are we talking about this? We were in a kind of interesting spot in early 2020. A lot of our systems are built with Elixir. And so this will be relevant to the community in the sense that that's what we're built on. But at the level of what this talk is about, there's going to be very little Elixir. So there's actually only one slide with code on it, and I might breeze through it. Anyway, where were we in 2020? In early 2020, our architecture sort of looked something like this. Please excuse my lackluster drawing skills. But our primary application was, from here on out, I'm going to call it the monolith. It had the majority of the platform's functionality in it. It's that big center square. It had almost all of the product logic, and it hosted the only API that was exposed to our customers who use our web and mobile apps, which are kind of hidden in that internet cloud. So the two pieces that were actually separate at that point were on the left, there's this withdrawals processing, which was separate for organizational reasons, that we wanted to stage withdrawals. They didn't happen immediately. They needed approval and checking by our compliance and anti-money laundering department. So that operated as a separate application that employees directly interacted with. And then off on the side, there's also the loan monitor. I mentioned the secured loans. As the price of cryptocurrency changes, so the notional value changes, we track that with respect to the amount of the loan that has been granted. And if the value of the collateral drops too low, we go into what is called margin call. We request our customers deposit more cryptocurrency or cash or some other thing to shore up the loan. And this ensures that we stay in good standing with respect to the amount of loan value that was extracted. So these were the three apps that we had running, aside from if you include the web app. And it was a pretty simple architecture. And this talk is about why and how we started breaking up this monolith. But early on, it had a ton of advantages. Foremost, it was the quickest way to get our products to market with a small team. Collaboration was easy because all the code was in one place. And so you could onboard engineers quickly, get them familiar with the system. Complexity was lower because you could see everyone else's work as it happened, and you didn't have to worry about interactions with other systems as much. We do integrate with third-party APIs and things, but for the most part, you had to only be concerned with the stuff inside this one application. You could also iterate more quickly on the code and the product and bring experimental features to customers sooner because it was, again, all in one place. And finally, scaling was simple. You just run more instances to get more capacity. Then you make your scaling limit the database usually. Now, additionally, OTP, Elixir, Phoenix, and Acto played a big part in our early successes. Their solid design meant that we could delay addressing many scaling issues that some other technologies would force front and center, and we'd have to deal with them. Instead, they were kind of just handled for us. Most of the code we wrote was sequential, just taking in a request, processing it in whatever way was appropriate, and returning a response. And we didn't require that much beyond what the frameworks had provided for us. However, things started to get rockier in late 2020, as it always happens when you experience explosive growth. And we experienced it. We got stonked, as they say. We had this growth both in our customer base and in our employee headcount. The growing customer base meant that bugs that may have been minor annoyances before became huge drags on customer support and on the engineers who are assigned to address those bugs. And on the flip side, the growing engineering team meant that there are way more cooks in the kitchen, and making coordination on efforts that much harder. Now, during this time, the size of our monolith application grew almost proportionally with the organization. We were shipping features really, really fast. And as a result, coding practices that in the earlier phase might have been sort of one-off experiments or special case scenarios sort of became how you do things. So complexity skyrocketed. On top of that, we had multiple high impact outages in a short amount of time. Because our customer base had grown so much, our tolerance for downtime became smaller, and outages caused outrages in support tickets and on social media. This meant our monolith had to be handled with extra care. The risk of making changes had ramped up significantly. And lastly, on the development side, things were also less pleasant. Features were reused across different product lines in unexpected ways because they just happened to be in the monolith. And that introduced hidden dependencies that we didn't account for initially. And we prided ourselves on having an extensive test suite, and it is still really extensive, but it became less reliable to run as more components had implicit global state that would affect other tests if run in particular orders. So they became flaky. And overall, the number of things to consider when making a change became too great. Instead of making changes in a small number of places, you had to consider many, many different parts of the system. So at that time in late 2020, our engineering leadership decided to undertake a project to re-architect our platform. So break up the monolith. The central part of that would be to decompose that monolith into the component product domains. Now, the goals of this were to address those limitations I just talked about. Primarily, we wanted to reduce the coincidence of failures. If one particular product domain had something that caused them to have an outage, we didn't want the entire platform to be down. If it stayed in a monolith, that would have been the case. Additionally, we wanted to improve the independence of teams. So if they're able to determine their own roadmap, they should be able to deploy independently and not have to coordinate heavily with teams to ship their features or their enhancements. And finally, along with the independence of teams, we needed to align the software architecture with the business in order to accomplish many of these goals. So in addition to just splitting up the code and the systems into separate deployable artifacts, we had to consider, are those artifacts aligned with what the business wants to do? So what are the areas of focus of this decomposition? The first one was actually started way before we really took on this effort in earnest. And our back office application was kind of the conjoined twin of our monolith. It was part of the monolith. It was deployed along with the monolith, but it served a very different purpose than our customer traffic. So we needed to decouple that. The second area was our accounting logic. So we wanted to unify the logic across all the products while making them independent of one another. This meant applying some practices that are well known in accounting, like immutable ledgers. And this kernel, so to speak, would be a single clearinghouse that's only responsible for moving currency across the platform between products. It would allow us to have regular reconciliation between products and find where our financial deficiencies are. And so this particular thing had to be really tight, focused, and well tested. There were plans set up to do a lot of quick check against it, chaos testing, you name it. But overall, like, this is the thing, the linchpin that the company would rest on. So it had to be a really core focus. The third area was customer data. So this one is a little bit less obvious, but it comes from the fact that we were running in a monolith. There's a list of customers, and those customers have associated accounts for various different products and cryptocurrencies. And so a lot of our product logic was based on foreign key relationships to that customer and loading that customer before you do anything, which makes sense in a monolith. But if you're going to have products deployed independently and they're not going to show your database, that customer data is not going to be in their own database. It's going to have to live somewhere else. So we decided that should move into a domain where it's organized by the compliance and client service departments, and the product accounting would be separate from them. We also had a big effort around load testing in QA. We needed to know that if we scaled 10x or 50x or something like that, that this new decoupled system would hold up, and that we wouldn't introduce new kinds of failures and performance regressions. So QA was a big part of that as well. And then lastly, hygiene, just generally improving our practices, trying to remove those things that were one-offs that became the standard way to do something, getting our database usage under control, and then adding observability to everything. So This is kind of the overview of how, the plan. Um, but one thing I haven't addressed yet is I've been talking about decoupling, but when you have separate systems and you went from a monolith, now you have distributed systems. And everybody who's been in the Erlang community for a while, or has been a colleague of me at Basho, knows that once you have distributed systems, now you have N problems. And you're choosing a whole different set of problems, right, than you do when you're running a monolithic application. So how can we actually make this work? What are the principles that we started out using and thinking about when designing this process? And here's where I want to get into resilience. I owe a great debt of gratitude to Jeff Hodges, who in 2014 wrote a blog post called Notes on Distributed Systems for Young Bloods. And this is kind of inspired by his blog post. So I've called it Distributed Systems for the Uninitiated. I think there are actually a lot of people who may have achieved senior engineer and never touched distributed systems. So not really young bloods. Okay, so I guess at this point, I need to define resilience. I love this quote. And I just happen to be so lucky that it happened to be shared on Twitter while I was working on this talk. And I highly recommend you follow Ruth Milan if you care about software architecture. She posts a lot of great stuff. So the quote says, there are two non-exclusive ways of dealing with possibilities: contingency planning and developing responsiveness. And this is a quote from Russell Akoff. And he is a pioneer, or was, I don't recall if he's passed away yet, but he's been a longtime pioneer in operational research and is best known for the idea of systems thinking. He's a good one to look up and read. The response to that was, that's a nice expression of robustness and resiliency and their differences. And the big thing to point out here is these are non-exclusive. You have to do both. So to summarize, we can deal with our problems in life, at work, and our software systems in two ways. We can plan for the worst, so contingency planning, or we can be flexible when things go wrong. Responsiveness, resilience. Now, if you're working with Erlang and Elixir like I am, you do get some tools to do both. For example, little things like pattern matching on OK error tuple returns let you cover all the possibilities of a bad state, contingency planning. And the let it crash philosophy, supervision, process isolation, let your system continue when you can't cover every case, or resilience, responsiveness. But for this particular architectural effort, we need to apply it at a higher level than individual bits of code and processes, and look at systems and their interactions. The truth is that distributed systems, as Justin Sheehy has said here, among others, are constantly failing. Richard Cook put it in another way, talking about safety critical systems, which are inherently complex, in his seminal article, How Complex Systems Fail, you may have heard of. He says, complex systems contain changing mixtures of failures latent within them, and complex systems run in degraded mode. So essentially what we're saying here is that since things are constantly failing, we can't ignore that. We can't just write the happy path and expect things to work. Errors are part of the new normal. Another way to think about partial failure, I think, was framed nicely by Eric Brewer and his colleague, Mr. Fox. I forget his first name, my apologies. In their paper from 1999, they say, we assume that clients make queries to servers, in which case there are at least two metrics for behavior: yield, which is the probability of completing a request, and harvest, which measures the fraction of the data reflected in the response. In other words, the completeness of the answer to the query. This trade-off is a subtler version of the CAP theorem you may be familiar with, but it was one of our guiding principles for our decomposition effort. The idea that we could improve yield, so improve the availability of our platform, by relaxing harvest. Imagine a request by a client that requires 5 components to fulfill. If all 5 of those components live in the same logical system, you've now correlated that failure. However, if they are independent of one another, you improve the possibility that unrelated failures won't cause the entire request to be unfulfilled. You can choose to return partial results. So how can we instead of being a victim of partial failure, how can we leverage our knowledge that things will be failing to build something better? Again, we go back to Dr. Cook. This is from his work on complex systems behind human error. You may have heard Fred Bear mention this in previous talks. Do give it a read. But they give us the way. They say enhancing error tolerance, error detection, and error recovery together produce safety. We can only create safe, reliable systems if we enhance these areas in tandem. So let's get a little bit deeper. Let's talk about some techniques you can actually use in your code to enhance these areas. So with respect to error tolerance, there are some obvious techniques. The first one that came to my mind is retries. It feels like the most obvious way to tolerate failure. If the thing you tried didn't work, maybe try it again in a little bit. It might work the next time. Another technique is buffering or queuing. And we're going to talk about this particular area of things a lot because they're all over distributed systems. But buffering and queuing are a way to smooth out the differences between types of work, especially when the resource you're protecting with a buffer or queue is flaky or has inconsistent performance. So you can use buffers to hide many faults from consumers of that resource. Now we know immutability well in the programming sense. In Erlang and Elixir, you create a piece of data, you only change it by creating new copies. But at the systems level, immutability of data means you can move forward with knowledge that you've already accrued, even if some processes fail in the middle. So for us, this is most impactful, and I mentioned it before, around our bookkeeping. Mistakes can be very costly when your ledgers are immutable. So only by accreting knowledge, and perhaps even in the case of a mistake made or an error that was introduced into your record, you can record retractions or corrections as new facts. And that helps us keep that system safe. The sister or brother to immutability is idempotence. If you pair this particular technique, so idempotence meaning you can repeat the same thing to achieve the same effect, repeat the same operation. If you pair it with retries, that can be a pretty powerful principle to make sure that your system can always move forward and remain correct. So finally, and I mentioned this, or I alluded to this in the previous slide, producing incomplete results. So producing a response that may not have all the answers in it is a way to choose yield over harvest. And then that way you can continue working even when some parts of your system are failing. Okay, so we covered error tolerance. Let's talk about error detection. Error detection, how do we find out that something went wrong? In the worst case, other systems, or maybe even humans, are going to need to detect problems. This is where observability comes in. Metrics, logs, tracing, monitoring, all these will help. One concrete thing you can do in your own Erlang and Elixir code is start adding telemetry hooks, even if you don't do anything with them yet. So measure the performance of things, measure the incidence of particular events that happen in your system. Jeff Utter's talk yesterday had some great examples of using observability to make decisions. So check it out on the recording if you missed it. Now, when failures come at you fast that you can't absorb, circuit breaking will prevent your system from doing unnecessary work. Now, I personally like using Jesper Lewis Anderson's Fuse library for this, but there are several good alternatives available in the community. Be careful though. Circuit breakers are tricky to tune. They require a good understanding of the runtime characteristics of your systems, so try to get observability done first. Now, this one may surprise you, but timeouts are an error detection technique. Timeouts are not errors themselves. In distributed systems, it can be near impossible to determine whether another system is down or just slow. So adding timeouts judiciously to your interactions means you won't wait forever. And propagating the problem to your own system and possibly others that depend on your own system. Now, deadlines are an extension of the idea of timeouts, kind of to the extreme, essentially giving a global timeout for every chain of interactions across your entire platform. They ensure that you never begin work that won't complete in time for the caller, and they rely on propagation in between systems to enforce. So there is a bit more effort involved than just creating a timeout. On the next slide, I promised one slide with code. I'll show you a really easy way to do timeouts in Elixir. But also please look at the deadline library on Hex if you want to look at deadlines. So here's our friend queues again. You really need to have bounded queues. Unbounded queues in your systems are the cause of so many problems. If you have to buffer some work, you limit the size of the buffer and let a full buffer, be a signal to related components that something is wrong in the form of back pressure or load shedding. And we'll talk about those more later. But things like bounded queues, resource pools, like your database connections, are just kind of different flavors of the same thing. They're controlling concurrency, essentially. If you're using Ecto, you get one built in, but you can also build your own in things like Nimble Pool and Poolboy. And there's a number of other resource pool-like things available out there. There are also plenty of queue-like things available in the community. I couldn't list them all. I think it's easy in Beam-based systems to kind of get lost in how effortless it is to do things concurrently and efficiently. And we sometimes forget that our systems have real limits, even if they're not directly visible. So if you use these techniques and you force limits in the small, it can lead to greater responsiveness and resilience in the large. So here's that timeout. I'll briefly describe this, but you can use this code basically anywhere. If you're writing sequential code and you're not already having a timeout with a gen server or something, you can use a task to spawn the work to be an asynchronous thing, and then you wait on it. And essentially you yield. So this line task yield is saying wait on this task until this timeout. If it succeeds, you'll get okay result, and you can return the result. If it does not succeed within the timeout, if it exits, for instance, you will exit, and you can pass on that reason to your caller. If it does not finish within the timeout, you call task shutdown, and that ensures that it cleanly shuts down and unlinks from your current process. And then you can return error timeout. This is basically the way that most Elixir libraries implement timeouts if they're not already doing something with like a gen server where it has a timeout on call. So make use of that. Okay, the third area is error recovery. This one I kind of struggled with, but the main automated techniques I know for how you can recover from errors tend to fall under the area of congestion control. In other words, preventing or coming back from overload conditions. The idea is that points in the system where work is introduced detect the overload and take action to give the system time to recover. So exponential backoff is probably the most well-known among engineers. It's like, well, did you do retries? Yeah. Did you do exponential backoff on your retries? Oh, yeah, I need to do that. The idea is if something fails, you retry it, but with a delay that grows exponentially. So you essentially give that target component that you might be overloading more time to recover. AIMD, or additive increase multiplicative decrease, is the technique used by the TCP protocol, sometimes known as slow start, and just generally speaking, congestion control. So with TCP and any other system that uses AIMD, as operations succeed, you increase the capacity or the measured capacity or concurrency additively. So you add one, you add two, something like that. When operations fail, you decrease the capacity multiplicatively. So you actually back off more than you grow. This tends to show up as sawtooth patterns in the capacity. You know, grow until you hit the limit, and they'll back off significantly. And you'll grow until you hit the limit. And that's sort of a steady state. A nice thing about this technique is that there are many fewer things to tune than static resource pools or circuit breakers, because the algorithm itself finds the limits dynamically. It's really powerful. Check out the regulator library on Hex PM for an implementation of this. Back pressure, which I might have mentioned before. is something people usually throw out when they're like, hey, you're overloading the system. Back pressure is an idea from control theory that systems will monitor their own capacity and signal to their input sources when they're overloaded. So preventing those sources from producing more work until there's more capacity available. I think the best example of this in the Beam ecosystem is GenStage, but there are lots of other ones. For example, there was a side job that Basho wrote a long time ago. But basically, GenStage kind of turns back pressure on its head. So it turns it into a pull mechanism instead of push, which means that the downstream components don't fetch work until they have capacity. So back pressure is most appropriate technique to use when you have cases you definitely want to complete all of the produced work, regardless of how long it takes. Back pressure makes sure that you can always, you can always do that later. So back pressure sibling, this is the last one on this slide, is load shedding. And this technique is for the cases where you can't complete all the work, especially where you don't control the rate of inputs. So a good example is web traffic. Very often you'll just have to refuse traffic when you have too much work to do. So instead of telling producers to slow down, with load shedding, the system uses some sort of heuristic to decide which work to abort. This is usually the oldest or the newest sets of work, depending on whatever your system goals are. Obviously, in web traffic, it's probably going to be the newest. Just like tell people to go away. I can't serve you right now. Okay, so with all those principles in mind, here's where we get a little personal. I need to tell you a little cautionary tale about some of our efforts. We let the dam burst. Our developers love Oban. If you haven't heard of Oban, it is a really well-designed background job processor that uses PostgreSQL for enqueuing and tracking jobs. We introduced it in early 2020 for a very narrow use case, but it quickly became the tool du jour for doing all sorts of asynchronous work. Everyone thought this piece of work absolutely needs to happen. It absolutely needs to be retried if it fails. I need guaranteed delivery. And so the answer was, well, Oban's there, use Oban. And I want to be absolutely clear, there's nothing wrong with Oban. I think it's a fantastic library when used correctly, but we started using it for even the most mundane types of reliability. We tended to confuse the tool itself with the technique it employs. So it has buffers, it has retries, it has back off. And that particular blind spot became a problem. Why is this a problem? Well, we gone and built ourselves a DDoS machine. As my colleague Gordon Guthrie put it, by design, Oban has no back pressure or load shedding on producers. So producers can create jobs as fast as the database will insert the rows. This means that if we use it really heavily for the wrong reasons, we essentially created a way to take our own systems down. Now, at certain times, we would see bursts of jobs being enqueued or worked on unexpectedly and stealing CPU time from serving customer traffic and loading down our database server. This has caused multiple outages. Some of the outages I mentioned that were in rapid succession were caused by Oban, or caused by our use of Oban, I should be clear. So this is a case where we had an architectural blind spot, and resolving this particular problem has been very difficult, partly because Oban is so easy to use. And I think that the detriment of not having back pressure or load shedding on the producing side has not sunk in with everyone yet. So I want to reflect a little bit in the last few minutes about how this effort has gone, what we did well, what went poorly, and what we learned. And I want to warn you, in the spirit of self-reflection, there's plenty of hindsight bias in these assessments. So take them with a grain of salt. Some things that went well. Since we began, developers, for the most part, have been building new services rather than building new components inside the monolith. So whenever there's a new business domain, we need to build software around, or some piece of functionality that was outgrowing its current state within the monolith. The engineering teams have really started thinking about how they can free themselves of those shackles, how they can deploy it independently, how they can build it independently and evolve it independently. And that's been a really good thing to see. On the flip side, we haven't been so good with communication. I think, this has been almost a year of effort formally, but being a company that was almost born, or at least exploded in the pandemic, we grew by hiring people extremely remote. This means we tended to have silos of communication. Our communication lines were just not really well and evenly dispersed. There was also some disconnect between engineering and the product direction, and that this decoupling effort, this decomposition effort was not a high priority for some people. And then this puts stress on the individual engineers and the team leads, who said, okay, am I supposed to build this feature that my product manager is saying, or am I supposed to do the decoupling like our VP of engineering is saying? Well, I don't know how to do that decoupling. That sounds complicated and hard, and it makes me think too hard. I'm going to build a new feature. So it, in general, it was difficult to get buy-in. I think we could have done a lot better on improving the communication, making sure it was directed at the right people in the right form. Another thing we kind of botched is we didn't do the most critical thing first. The newly proposed accounting system took many months to even get to prototype stage. And unfortunately, it was built by a single, very senior, but single developer, which is probably not the right way to ship this kind of component. I believe now it should have been built by a team with stakeholders from all the major products and a clear transition plan. Regrettably, I think we still have a lot to figure out here still. There still is a very strong possibility that we complete this project. We are definitely not done. And I alluded to this earlier, but one thing we definitely learned is developers will prioritize easy. The Oban incidents showed us that they really just want the easy way. So the best way to get them to adopt good practices is make those things easy to employ. So make the good easy to do. Now, we did take advantage of this understanding when we started standardizing the HTTP clients we use internally. The Elixir ecosystem has lots of different HTTP clients, and we basically used all of them. But by giving developers one that comes with a lot of the things we want, for example, per target connection pools, so that there's not contention across multiple destinations, retries, circuit breakers, all these things I've talked about already, observability. With those built in, they don't have to piece those things together themselves because they would be liable to do it inconsistently. And we did the same with metrics and monitoring and logging and dashboards and things, and that has been working very well by standardizing on single tools and really advocating for those things to be easy. One thing that we didn't recognize at the early part of the project was that partial failure is also a user experience concern. Your user interface has to consider that. It has to even go back as far as design. So your designers need to be thinking about what are the functional components of this user interface. What should I show if something fails? And that has to be built in from the beginning. Now we're kind of retrofitting a lot of that, and it takes a lot of work and redesign. Finally, I'm going to borrow a phrase from our friend Chris Keithley and say that I've been thinking about it a lot. I'm convinced that decoupling is not a thing. It's not a thing. It's a rewrite. We had full-on second system syndrome, but we also kind of did it in the hardest way possible. We tried to be incremental and very careful not to break things along the way, which makes sense from a business perspective. But we also didn't get it all started at once, and in the same way. So we didn't recognize that it was a rewrite, and that became kind of a sticking point. The other thing is that the goals of this project were only partly technical in nature. The largest change we needed to make was to our engineering culture, how we communicate, how we get things done. And that has only a tiny technical component to it. Honestly, all this change is probably too much for folks. Even if they bought into the technical vision of having a decoupled system, change is really hard. It requires a lot of coordination and a lot of buy-in. Thanks to Conway's law, your systems, if you go to take on this kind of effort, it probably already reflects your communication patterns. So maybe, please learn from our example. Try to exploit those communication patterns instead of fighting against it. Your other alternative, which I think we attempted not so successfully, was to create the communication patterns you want that will produce the system that you want, and then set up your technical change. That's about all I have. Thank you so much for listening to this very non-Erlang Elixir specific talk. You can reach me on GitHub and Twitter, Sean Cribbs, basically everywhere. And you can already find these slides, including all the notes you can't see, up on my website. So hopefully that's readable enough. And again, thank you for your time. I hope there's time for questions.
Ask Barbara that.
Maybe for one or two.
Good. There's only one question, and it's from Eric Saxby. Do you want to unmute yourself and ask it?
There we go. I can unmute myself. I'm curious if there were any other sort of operational tools or just, accidents of time that came in that allowed you to put things off. And in my experience, PG Bouncer is generally like proxies like that tend to just slot themselves in. And I'm wondering if there are other tools that helped, or just changes like hypervisor changes in your cloud provider, things like that.
Yeah. Around the start of this effort, we had already started, like early 2020, we started working on redoing our infrastructure. And I think it has its own warts, like we kind of traded some problems for others, but a big level up that we accomplished was we switched our deployment process from these kind of manually constructed Ansible playbooks to some more infrastructure as code using Pulumi. And the sorts of efforts that the infrastructure team were able to do to factor out the things that were common among all the applications, make standard ways to set them up, that really helped. There's some aspects of it that I think are probably too heavy-handed, but we're continuing to evolve that, and it makes it actually easier to make those changes. You mentioned PG Bouncer. We have considered that, but only as like an infrastructure level reliability concern. We do heavily make use of Ecto. So a lot of cases where you're using PG Bouncer, you're trying to abstract away whether someone's using a read replica or not. You're trying to provide like connection pooling at like an infrastructure level. We didn't really need that because we were always using Ecto. But it has been considered for cases where we might want to do send queries to read replicas instead of the primary. We just haven't scaled beyond that right now. So I think we may have encountered that in the future. Thank you, Eric.
Cool, thanks.
Are there any other questions?
I'll take it while Amos
Hi, Torben.
allows it. When are you writing a book, please?
See, a couple of months ago when I was proposing this talk and thinking about it, I was like, this sounds like a great book. Maybe someday. Maybe when my plate's a little bit less full.
Yeah. And by the way,
suggestion though, Torben.
Yeah, Neotoma rocks or squeaks or whatever.
Oh, thank you.
Yeah, it just works.
Yeah, it has some pathological edge cases that are pretty bad, but it does work for those little small languages that don't work with regular expressions.
Well, I had a go with it last year on implemented a SQL language with it, and I hammered it with quick check, and it was not Neotoma that caused the issues. It was somebody else. I don't know who, but not
That's good to hear.
Yeah.
That's good to hear. Thank you.